Consider the circuit shown below, where C1 has a capacitance of 8 microfarads, and the capacitance of C2 is 1 microfarad. The delta V of the battery is 19 volts. S1 and S2 represent switches which can be arbitrarily opened or closed in order to let charge flow. First, capacitor C1 is charged by the closing of switch S1. So let's draw what that'll look like. First of all, it's worth noting that in a circuit diagram, the long line and the short line is the symbol for a battery. And the long line is actually the positive terminal of the battery. So we can redraw it like this. And now switch S1 is going to be closed, so that's going to allow charge to flow through that path. But switch S2 will still remain open, and it won't be closed, so charge can't flow through that path. One of the primary problem-solving techniques that we can use here is to label different points around the circuit what the potential values are. Okay, and some of the most important points would be the terminals of the branches and also the capacitor plates. We want to know what voltage they're at. Okay. So I'm just going to label the negative terminal 0 volts, and I'll label the positive terminal 19 volts, because that's what they said the delta V of the battery was. All right, so we see that these 2 points are in direct contact through a conductor with the battery's positive terminal, so we're going to want 19 volts at both of these points. Okay. All right, down here we'll have 0 volts. And this is going to be 0 volts here. All right, so since the opposite side of C2 is not in direct contact with the battery will not push negative charge onto C2's negative plate. And for that reason, we're going to say that C2 remains uncharged. If it remains uncharged, then there must be no potential difference across it. C1 is going to be charged, and we can see that there's a huge potential difference across it. That means there will be a strong field inside that capacitor. But we're only able to create this condition because C1 was in contact with the negative terminal and the positive terminal, which allow the positive and negative charges to pile up on the plates. A field won't develop inside C2. And since this part of the conductor is also in contact with that same point, it will be at 19 volts as well. All right, let's calculate the initial charge acquired by capacitor C1. So C1 has a capacitance of 8 microfarads. We can use the capacitance as well as the delta V across that gap to find the Q. So it's going to be 8 microfarads times 19 volts. $152 microcoulombs then. All right, now switch S1 is going to be opened, and the charged capacitor will be connected to the uncharged capacitor by closing switch S2. All right, so let's just draw it one step at a time here. First, we'll open switch S1. And let's see what our potentials will be like around the circuit now. We'll have 19 volts at the positive terminal, of course. We'll have 19 volts at the positive plate of C1. And we'll have 0 volts on the negative plate of C1. This is what happens when the capacitor has been charged. There will be a potential difference across that capacitor. All right, so this will be at 0 volts. The negative terminal of the battery is 0 volts. The switch is at 0 volts. And there'll be no potential difference across that gap. Okay. This will be at 0 volts. Over here, we're going to still have this guy at 19 volts. Our capacitor is uncharged, so there's no potential difference across it. So we'll have 19 volts and 19 volts. When we close this switch S2, that's going to allow a path for the electrons to flow. Okay, so let's see how they'll flow. All right, so all of these points are still going to be at 19 volts. But now we have to find out what potential this lower portion of the circuit is going to be at. It may not be 0 volts anymore. So how do we figure out what it will be? Well, we have to look at how much charge was on C1 initially. We calculated that it was 152 microcoulombs. We have conservation of charge, so those charges cannot be created nor destroyed. But what's going to happen is they are now going to be allowed to flow to the other capacitor. And it might not be half and half. Okay, it might be that just some of the charge flows over to capacitor C2. It's all going to be based on its capacitance. Okay, some capacitors are more capable of holding larger amounts of charge than others. All right, let's find the equivalent capacitance between these two capacitors. Now they are in parallel. Why? Because our positive terminal is connected to both of their positive plates, and our negative terminal can potentially be connected to both of their negative plates. They're in parallel, so we want to add C1 plus C2 to get the equivalent capacitance. So according to the givens, C1 was 8 microfarads and C2 was 1 microfarad. So it's a total of 9 microfarads. All right, now if we wish, we could redraw the setup using a single equivalent capacitor. Because in effect, that's what we have here. There's two plates which both have large areas, and they're both connected to each other through metal. So it's like as if they're one large plate, a 9 microfarad plate. Okay. So with that in mind, let's figure that we're going to have 152 microcoulombs on this equivalent capacitor. Okay. From that, we could find the delta V of the capacitor. We'll just use the formula CEQ equals Q over delta V. So we'll have 9 microfarads, 152 microcoulombs over delta V. Solving this, we get delta V equals 16.9 volts. So that is going to be the new potential drop across the gap. Because remember that the delta V of the equivalent capacitor equals the delta V of the first capacitor, and that's equal to the delta V of the second capacitor. They're all the same delta V. What we can do now is we can subtract to find out what potential the negative plate is at. All right, if our delta V is 16.9 volts and our positive plate is at 19 volts, then let's just subtract. And we get that our negative plate is at a potential of 2.1 volts. And that's going to be in common for both of them because they're in contact and they're in electrostatic equilibrium. All right, now that we know the delta V for both of these, we know that each of the delta V's is 16.9 volts. Now we can go back and solve for how much charge must be on each of these capacitors. One of them can hold much more charge than the other. The C1, that's an 8 microfarad capacitor. C2 is only a 1 microfarad capacitor. So actually C1 is going to hold much more charge than C2. But let's calculate how much it'll be. We'll use Q1 equals C1 delta V1. All right, so we'll have 8 microfarads times 16.9 volts. It's going to be 135 microcoulombs. Now remember that C1 used to hold 152 microcoulombs when it had a potential difference of 19 volts across it and it was fully charged. Now some of those charges have been allowed to migrate to C2. And this will lower the total charge on C1. It'll lower the field strength between its plates, and it'll lower the potential difference across it. Let's figure out how much charge is on C2 simply by subtracting. Take the 152 microcoulombs and then subtract your 135 microcoulombs, and this will give us Q2. It's 16.9 microcoulombs.